You see anybody waiting for? Let me start. And
spectroscopy.
You got two computers going.
Yeah, the hub is one, and then I'm the other one. It's very confusing.
Technology.
Putting it together right now.
There has to be a better way.
There's going to be a lot of
This is meant to be
tools.
Brett, like
Yeah,
try a little
yeah,
Brett.
Physics department has like a Zoom room. So there's just like a little
It's a part of
screen and you
the,
just
it's
hit
a part of
go, and
materials.
then it, like,
Awesome.
It will
is
be in
awesome.
material science, but eventually
That's like the
maybe
innovation hub downtown.
somewhere else.
Yeah, it's way
It's the same
easier.
idea. Yeah, but
It's-
physics has
It's
one.
a part of the ARC
That's awesome.
proposal
It's of course all
that
this book.
Suzanne Money and
Yeah.
Josh and I wrote
I
for
can
like
see that.
training workforce development.
For the credit minor that she was.
One credit.
No, but that
Hey, Anthony.
for the
Thanks for
credit
coming.
minor that she proposed, right? You're talking about Suzanne
Someday
Money?
maybe.
Suzanne Money?
It may be a minor someday. I mean, like that's
Suzanne Money,
Suzanne
right?
Money, yeah.
She was talking about the
Mhm.
credit minor and
Yeah.
I mean, that's like,
Mhm.
that's like the long vision.
Mhm.
If it gets there, that'd be cool.
If it gets there.
Yeah.
Be
I thought it's
optimistic.
kind of already on the way.
Nope.
No?
I mean, we don't even have classes yet. I'm making it right now.
Yeah, I talked to her a couple weeks ago about it, and she said she was trying to figure out like the best way to make it happen.
But
I think
there
we're
are,
making a roadmap.
there are many
Exactly.
existing.
I mean,
I'm
it'd be
gonna go
great.
ahead and
I think it'd be really
close
great to have a minor for that. Yeah.
You should also email Mark Horn
Mark,
or someone. Because they are in charge of the master nano master in nano
oh, okay.
in our department.
All right, so let's go ahead and get started so that we don't end up, behind schedule to start with. So my name is Stephanie Law. I'm the Director for Education and Outreach Programs for the 2DCC. So thank you all for attending our RSVP Symposium. So I'm here with Kelsey, who is the staff person who works with all of the education and outreach stuff, as well as does a bunch of other awesome stuff. So for those of you who are not familiar, the RSVP program stands for Resident Scholar Visitor Program. And the idea with RSVP is early career folks, so graduate students, postdocs, or early career faculty can apply to RSVP. And the application consists of a project description of what you would want to do if you came to 2DCC. And then if your project is accepted, you can come to 2DCC. We help out with travel and housing while you're here. And you can spend some time in the 2DCC working on the equipment that we have here. So you can work in our thin films facility or our bulk growth facility, the Chet facility, and so on. So you can look online and see the different facilities that we have. It's a really nice program. So you'll hear today from some of our previous RSVP scholars about what work they did while they were here at Penn State, as well as some of the outcomes of that work. So the next deadline for RSVP is the end of January of 25. So if anybody who is listening online is interested in applying for RSVP, please note that deadline. And if you have any questions, you're welcome to send me an email or reach out to Kelsey. We'd be happy to talk about RSVP with anyone who is interested. I should note that the RSVP program, as well as the 2DCC in general, is generously supported by the National Science Foundation. All right, so our first keynote speaker is Jonathan Chin from Georgia Tech. So he was here in summer of 23, working in our thin films MBE facility. And he's going to be telling us about the impact of substrate and selenium concentration on the morphology of MBE growth tin selenide thin films. So Jonathan, whenever you're ready.
Hey, thank you very much. Let me share my screen. All right, wrong one.
Okay, is that showing the right thing now?
Perfect. Thank you,
All right,
Jonathan.
thank you very much. Okay, so good afternoon, everyone. Again, I'm Jonathan Chin. I was a RSVP visitor in 2023, and I'm going to be talking about growing tin selenide thin films. So just some background on tin selenide. So tin selenide is a piezoelectric material, where you can, it's not, oh, I forgot to remove that. So a piezoelectric material is one where you can transduce a mechanical strain into electric current and vice versa. Now, tin selenide is predicted to have a higher D11 piezoelectric coefficient than comparable lead-free piezoelectric materials like aluminum nitride or quartz. And it has a predominant polar direction and along its 0, 1, 0 direction. So if you were to apply a force, so like so if you apply a force, you will get a strain in the material. This polarization will change, and then that's how you can generate your current. So tin selenide is a layered material, so it has van der Waals bondings, and its unit cell consists of what I call these two individual layers. And the polarization direction in each individual layer is going to be in the reverse direction. So because of this central symmetry in bulk, multi-layer tin selenide should not have any piezoelectric effect. But if you were to reduce this into one layer, so which would be half of a unit cell, that gives you your predominant polar direction. So this is one of the reasons why we need to have layer control in tin selenide. So if we want to access this piezoelectric effect, we need to have this single layer of tin selenide. So this kind of brings us into the goal of my research project, which is to grow thin film tin selenide with the proper dimensions for piezoelectric analysis. So there are three objectives we need to accomplish this. The first is we need to figure out what substrate we want to select to grow on so that we can align to access that unique polar axis. We need to be able to control the morphology. So we need lateral areas large enough for device testing and manufacturing. And then we're going to need planar growth. So we need to have our atomic scale layer control so we can get that monolayer or and control the number of layers we have. And we can do these by we think we can do these by changing our selenium concentration to our flux ratio and the order in which we open our cells. So everything was done at the TDCC coccogenide molecular beam epitaxial system. I was hosted by Professors Stephanie Law and Maria Hilse, without whom this research would not be possible. So recap on MBE. So we have our vacuum chamber, which can go to ultra-high vacuum. There is a heater which rotates, upon which sits our substrate. And we can have our fusion cells of our tin and selenium sources. We heat those up, and our molecular beams kind of hit our substrate. And we can monitor this in situ with reads, which allows us to monitor the growth of these films. And then we can check the temperature with our infrared camera. So one of the first steps to growing our film is to first figure out what substrates we want to grow on. So one of the challenges is that tin selenide has a very high binding energy. In comparison, MOS2 has a binding energy of 23. This has a binding energy of 146. So what this means that a high surface energy and lattice match should encourage the planar growth of this material. So we looked at four different substrates that have close lattice matches and that have been used for thin film materials. So this would be A-plane sapphire, C-plane sapphire, mica, and magnesium oxide. And here are some examples of growths that under some same conditions that have been found on each of these substrates. And what we can see is that on both sapphires, so the aluminas, we do have grain growth, but it's not on A-plane sapphire, it's not continuous across the surface. On C-plane sapphire, we do have that continuous surface coverage, but we have a lot of out of plane. We can see in the read patterns by the streaks or by these rings, and these rings indicate that we have these polycrystalline growths, which essentially means that we have no predominant in plane orientation, and we're kind of growing these outwards. So it's not exactly what we're looking for. In the mica and MgO, however, we do kind of see these streaks. It's more clear on the MgO where we see this predominant in plane orientation along the 0, 1, 0 direction. So now, if we look at our MgO in more detail, so one other thing we need to consider is the substrate preparation. So we have cleaved, annealed, and cleaved and annealed. So what does those mean? So cleaving our substrate is when we kind of split the substrate in half so we can grow on the inner surface. Growing on this interface gives us a more clean interface. So we're going to have a better, potentially better lattice match, and we may be able to avoid some of those surface hydroxides and carbonates and things that will readily adhere at MgO. Annealing, so going to high temperature, like we're setting for 900. We think we were getting around 700 degrees Celsius. We annealed that for about 10 minutes, and this allows us to kind of burn off any of those excess carbonates or hydroxides that are left over on this face. And when we do both of these steps, we find that this is what allows us to access the this nice like smooth morphology where we have this predominant in-plane orientation. We have these individual layers, which you can see these kind of grains that are growing on top of each other, and each one of these has a step height of that one layer, so that half unit cell. So some next steps are going to be to try to isolate this, where instead of growing nucleating these additional grains on top of the underlying grain, if we can grow just that underlying film without the excess, that would allow us to establish that layer control. So flux ratio. So when we are growing these films, if we were to deposit one-to-one like stoichiometric, like tin and selenium sources, like in the red, we would end up getting some excess of tin. And one of the issues is that selenium is just a highly volatile material. It's going to readily desorb from the substrate as soon as it arrives. So we need to oversupply our selenium. So one of our initial checks was to determine an optimal flux ratio so that we could access the stoichiometry we need. So we're trying to get PNMA tin selenide, which is the one that's going to be piezoelectric. And we find that around this 1.35 selenium to tin ratio is going to be a bit of a sweet spot to access the stoichiometry we want. And we can see here some XPS. So this is an XPS, X-ray photoelectrospectroscopy depth profile of that sample, where we can see that we are maintaining this one-to-one tin selenium stoichiometry through the bulk of material until we hit the magnesium oxide substrate. And so one of the things we can do where if we see like when we grow these samples for 10, 30, 60 minutes, that's where we have our nested morphology. But when we grow for very short periods of time, the morphologies are going to look very much different. So we have these individual nucleated grains that are at some point expanding and coalescing into the underlying films. So one of the things I'm looking, we start to look for is how can we access this more continuous layer earlier so that we can access that single monolayer. And this is where we turned into growth order. So by growth order, this is going to be the order in which we open our effusion cells. So previously we had done tin and selenium simultaneously. So that would be the top AFM image. And we found that if we pre-supply the system with selenium, this decreases our average step height. So now we're able to access grains for the same time or for the same growth time. We can access grains that are shorter, and there are more of them. So our nucleation density also increases. So what this suggests is that by having this additional selenium, this may provide a route to kind of having more grains that may coalesce earlier. This is work that we're still working on analyzing, and this is still in progress. But these initial results are promising. So it may lead to a way for us to get to that single monolayer where we have that continuous layer across the substrate. So this is the result of that growth. So we have that selenium first, and this is we managed to find a time in which these do coalesce into this layer. Now we did some XRR on this sample. This is our most smooth and flat sample. It is still around 5 nanometers in total thickness, which is going to be around 10 individual layers. But what we can see here is that we have these individual grains where you can see the grain boundaries between these different structures where they have developed and then coalesced into this continuous underlying layer. So this is where we want to kind of continue off of moving forward, where if we can get to this coalescence earlier, we can get that thickness, overall thickness down to that monolayer limit, and we can test it for piezoelectricity. So recap our goal, we're trying to grow these tin selenide thin films for piezoelectric measurements. We need to control the orientation so we can measure piezoelectricity, which is again in one single polar direction. We need the morphology so that it's wide enough so we can deposit electrodes and do that piezoelectric testing. And we need to control that layer count. So we've established a method to isolate PMMA tin selenide with that predominant in plane and orientation in magnesium oxide. Other than that, we can adjust our selenium concentration through flux ratio and growth order to help increase our overall grain areas and decrease our grain thickness. And we've published some of these initial results in a couple of papers now in nanoscale and MRS communications. And we have 2 more in progress on the work that's been presented here on substrate selection and growth order. So finally, I would like to thank staff at the 2DCC, particularly Stephanie Law and Maria Hilsey for hosting me and training me how to use the MBE system. I'd like to thank the research staff scientists and the other support staff at the 2DCC who have just helped to enable like the entirety of my thesis research, without whom I couldn't be doing the work that I'm doing. So thank you all very much.
All right, thank you for an excellent talk, Jonathan. So we have some time for questions. So if you're online and you have a question, you can just unmute and speak up, or anybody in person is also obviously welcome to ask a question. Yeah.
Yeah, so I had a question for you. In your conclusions, you stated that the MGO substrate, I don't know if you said it was the only one that provided in-plane growth, but how did you show out-of-plane growth, or was there evidence of out-of-plane growth of the tin selenide film on any of the substrates?
So in our XRD, we can see that we do have predominant out of plane in the 200. So this is focusing on tin selenide on MGO, where we can see the out of plane with 200, 400 orientation. So that's where we're going for this kind of middle. So around this 1.35 flux ratio. Once their flux ratio increases too far, we start getting these 201, 311 orientations.
Okay. Did you test the other substrates, or you just tested magnesium oxide? Because
We
you're
did
getting
test the
large?
other substrates, and they tend to have additional phases. I just didn't show them here.
I see.
Other questions? Yeah, Sloan.
Do you know anything about the orientation of the layers with respect to each other? Are they twisted? Are they aligned?
So I didn't hear the first
I'm
part of
sorry.
that.
So I'm asking about the lattice matching, lattice orientation in the subsequent layers. Are they twisted? Are they fully aligned? Are they shifted?
Oh, okay. So that's something I still need to look into. So right now we're just looking at the calculated 1D like lattice mismatch.
Thank you.
Have you done, I can't remember, Jonathan, did you do any measurements to look for like twinning in your film? I mean, X-ray bi scans or anything?
Yes. So we have done some like in plane XRD if that's what you're asking. But right now we're kind of seeing like we're predominantly just seeing that twofold orientation between with the orthorhombic tin selenide. I haven't seen any particular like effects like that, but there's something that's also not something I've particularly looked into either.
Right. All right, other questions for Jonathan?
It's just curious that the magnesium oxide was like the best substrate. If you go back to the first table, like the lattice mismatch and the surface energy were, maybe the surface energy was low.
So the mismatch is
The mismatch is low.
Yeah,
Okay.
one thing that we're thinking that may be helping with the surface energy, and something I'm still trying to work with theorists to simulate, is that perhaps the cleaving and annealing preparation steps for MgO is increasing the surface energy higher than those same effects are on the other substrates. So we may be, so this is the surface energy of like MgO as prepared. It may be different when it's in our vacuum chamber. So, but that's something we're still trying to like determine the exact dynamics of.
We have time for probably one more question. Anybody have one more question for Jonathan? Yeah, you might have to speak up.
How do you cleave the MgO? Like, how did you exactly do it?
Yeah, we
How did
use
you-
a razor blade or a scalpel, and we just kind of go along one of the sides, like at the corner. We press in, and we're able to kind of snap the substrate in two pieces. Just for clarity, this is like a hamburger, so like our sandwich, can split in two slices of bread that way. So we're not cleaving it like down the face, so it's not normal to the face, it's parallel to the face, if that makes sense.
Yeah, thank you.
All right, well, let's all thank Jonathan again for an excellent talk. I should mention Jonathan is going to come back and visit us again next month. So again, if anybody's interested in coming as an RSVP scholar, that does not have to be the end of your interaction with 2DCC. We're always happy to have people come for follow-up research. All right, so our next speaker is Anna Sheets from University of North Carolina, Greensboro. So Anna was here this past summer working in our Thin Films MOCVD facility. So Anna, feel free to go ahead whenever you're ready.
Hello, my name is Anna, and I'm going to be talking about the modulation of inherent properties of 2D devices by strain and doping engineering. I want to actually let me go to the next slide. Sorry. If we want to skip me for now, because I am having computer problems. It actually won't let me do anything on my computer.
What's that?
We could go to Sam and James.
Okay, yeah, so we will come back to you. So Sam, are you there? Are you ready to go ahead? Okay, good, you are there.
Yeah, we'll be good.
So we will go ahead and move forward to Sam Oyan from Florida International University. Sam was also here this past summer working in the bulk growth facility. So Sam, take it away.
Alrighty, everything look good here, or?
Great. Yep, thank you.
Perfect. So I'm Sam. I'm also going to be presenting alongside with James, who also worked with me with the Dr. Mao group, and we'll be presenting on high entropy materials with a 2,4,5 chalcopyrite structure. Okay. So a little bit of background on the chalcopyrite materials that we were studying. We have 3 parent compounds that were synthesized experimentally: manganese silicon phosphide, zinc silicon phosphide, and magnesium silicon phosphide. These are direct bandgap materials that are in the space group 1,4 bar 2D, and they are diamond-like. What is very much of interest with this diamond-like crystal structure is that it is non-centrosymmetric. This is especially useful for nonlinear optical applications, which are required, which nonlinear crystals allow for frequency conversion. To grossly oversimplify frequency conversion and nonlinear optics, essentially, let's say we have a green laser that we're shining through our material. As it comes out of our material, we might get a red laser with a specific wavelength or some other color laser that would come out of that material. This is especially useful for a lot of wide range of applications. As mentioned, first, the lasers, obviously. This is especially useful for medical imaging equipment. It's useful in telecommunications, and a little further down the line as well, there's a lot of interest in applying it for quantum computing as well. And while we were looking at the parent compounds, our point of interest for the RSVP during the summer was introducing high entropy into these parent compounds. And the reason why we wanted to do high entropy is that they have, on average, they have higher compositional uniformity, similar to their parent compounds. And because there's a lot more elements that we're introducing to the crystal structure, there's a lot of local inherent disorders and asymmetries, which allow for a bit more fine tuning of certain parameters. In our case, we wanted to fine tune the band gap of the high entropy materials with respect to their parent compounds. So to sort of explain a little bit of how high entropy works, essentially by adding a lot of these different elements into the compound, in our case, or actually not in our case, a lot of literature suggests that sort of the magic number that works for really minimizing a lot of the Gibbs free energy of the system is 6 to 7 elements. And by adding those 6 to 7 elements into that crystal structure, we are greatly increasing that S term, the entropy, which in turn decreases the Gibbs free energy of the entire system. And because that Gibbs free energy is minimized, it makes it a lot more likely to form a single phase of the high entropy material that we're interested in studying.
All right. For our project, our goal was to successfully synthesize the crystals with desired molar composition of each element and attempt to develop a method to reliably reproduce these compositions. And then after synthesis, obviously we characterize using EDS from the SEM just to confirm that the atomic percentages were what we would expect of those molar compositions that we had synthesized them with. And then further characterization of the crystals, especially UV vis and SHG is needed. These were actually done due to time constraints by one of our mentors, Yasu, who sent us the data afterwards. And then as a secondary goal, we also wanted to try and attempt to predict the material behavior using computational studies in DFT. But I'll talk again in a bit about why this isn't or was not exactly possible for us in the amount of time that we had access to. So starting with the computational methods, the first thing that we did was just a base level DFT simulation, very bare bones, no special parameters on anything, just to see how the properties would match that reported in literature for the parent compounds. And then after that, we move on to DFT with a Hubbard correction, or DFT plus U for short. And this is kind of a way to empirically get physical properties, especially band gaps for the materials, while saving a bit on computational resources. And lastly, if we're still not able to reproduce the desired properties, we move on to hybrid functional calculations, which are very resource intensive. So when I was talking about the resource intensivity of these calculations, this is just a comparison of one of our compositions compared to the parent compound MSP. We can see there's tens of hundreds of times of more individual atoms that would need to be simulated in the unit cell. So it's pretty obvious why in the time constraints that we had, it wasn't exactly possible to calculate the high entropy material itself. And additionally, you wouldn't be able to just run this calculation once. You'd likely have to run it several times and take the average of those values. But not all was lost. We were still able to simulate a couple of the parent compounds to gain some insight into band structures. Starting here with magnesium silicon phosphide, we have here on the left the band structure. You can see, comparing to literature, the direct nature of the band gap is recreated here in the simulation, with the band gap 2.33 from literature, almost exactly replicated here, 2.32 EV at the gamma point in the Bruin zone. And on the right, we have the density of states, total density of states, and then also broken down into the major orbital contributions from each of the individual atoms. And it's a little hard to see exactly the valence band and the conduction band, so I have them zoomed in here on the next slide. And we can see that the major contributor in the valence band is the phosphorus p orbital. And meanwhile, the conduction band has slight contributions from all of the ones listed, but for the most part, it's the silicon p orbital and the magnesium p orbital. Moving on to the manganese silicon phosphide, we can see a bit more complicated band structure and density of states. And that's actually because we expect this material to exhibit some magnetic properties. So you actually have to do a special kind of calculation called the spin polarized calculation. And that separates out spin up and spin down states for the electrons and considers them individually, right? So on the left here, we have the spin up states highlighted in blue with the conduction and valence bands highlighted in red, and then the spin down states highlighted in green, conduction and valence band highlighted in yellow. And you'll also notice that I've listed 3 band gaps here, and that's because for the total density of states, or sorry, not total density of states, the total band gap, that's just considering both spin up and spin down, which was only 0.72, while the band gap for only the spin up states was shown to be 1.47, which was very close to the experimental band gap of 1.5. And then lastly, the spin down 2.47. And then on the right here for density of states, on the right, in the positive portion of the graph, those represent the spin up density of states, while the negative represents the spin down density of states. Because the spin up density of states was the one that best replicated those of experimental values, those are the ones that we will be zooming in on to focus on the valence and conduction bands. So breaking down the valence band here, we can see that, again, similar to the magnesium silicon phosphide, phosphorus p orbital in the valence band is the major contributor, with also a pretty significant contribution from the manganese d orbital, as well as some minor contributions from the other ones. And then on the right, the conduction band, some contributions from everything, but this time the major contributor is the manganese d orbital, with also some slight contributions from silicon p orbital, manganese p orbital, and also phosphorus p orbital.
So now that James has kind of summarized a little bit sort of the computational results that we were able to gather, we can now move on to the synthetic results, or the results that we got from our time at Penn State. This project sort of broke down into 2 different compositions of interest. The first one, Project A, looking at substituting a lot of alkali earth metals in the magnesium spot for the magnesium silicon phosphide. One of the main things that we wanted to see is the influence of magnesium. So you'll notice that for lot number 2 and 3, there's a drastic increase in the weight percentage of or atomic percentage of magnesium with respect to the other elements. For Project B, we're sort of just looking at incorporating more transition metals, and especially the manganese, as James mentioned, that the manganese introduces some interesting magnetic properties should the crystals crystallize in the high entropy phase that are of interest. So to sort of explain a little bit of how this process sort of went with a graphical scheme, first we loaded these elements in stoichiometric amounts in an inert atmosphere in a glove box, and that was then loaded onto a crucible. We used antimony as a flux, and that was then loaded onto an ampule. This ampule is then taken out of the glove box and is taken for necking and sealing. During the sealing process, it reaches vacuums of up to 10 to the -4 torr, and once it is fully sealed, we are then able to place it in a furnace. The growth profiles for these are a ramp up to 1100 degrees C, a controlled ramp down to 900 degrees C, and overall this entire growth process is about 8 days, give or take, maybe an extra day depending on if the growth was set up before a weekend or anything like that. Finally, these ampules are centrifuged to separate the antimony flux from the crystals, which allows us to break the ampules to recover the actual crystals. For project A, what you'll first notice is actually there are some tacks or dashes on some of the compositions. This just means that these elements didn't incorporate all too well into the crystals that we were able to recover. And even though some of them do have the whole gambit of elements, number 4 especially has all of them presenting, it's not really in the ideal atomic percentage that we wanted for that particular composition. We'll go on a little bit later to explain why we think that may not have worked, but we'll move on to a little bit of UV-vis spectra that was provided by our mentor Yasu, and we can see with A2, crystal A2 and A3, that there's some clear absorbance as we enter the visible spectrum, and the crystals actually formed relatively nicely. Granted, there's always going to be some antimony or some other secondary or tertiary phase material that can be presented, even alumina from the breaking of the crucible on the crystals that can influence compositional analysis. Here are a few more crystals, the A4 and A5 samples, and again, we see clear absorbance in the visible spectra. To sort of compile all of these results, we only highlighted a few of the UV-vis spectras, but we did get a few more crystals from that. And these are compositional results after polishing. I should have mentioned before, UV-vis was taken after polishing the samples, and some of these crystals obviously don't survive the polishing step because they're either too small or and they damage very easily, or they're just too small to provide any valid data that could be reported. However, with the crystals that we were able to image and get UV-vis spectra data from, we were able to identify a trend between the magnesium with respect to the total magnesium and zinc content. With the ones that were imaged, we found that with an increasing amount of magnesium, there is an increase in the band gap. This relates, or this is sort of validated by an R value of about 0.9, so the trend is pretty strong. A little bit of discussion on why some of the Project A samples were a bit difficult to fully synthesize. One thing we expect could be the cause for the high entropy phase not really incorporating the way, or crystallizing the way we wanted to, is that there is a very large difference in the atomic radii of the elements, especially since we're just going down the column of the alkali earth metals. I think the greatest range of difference between the atomic radii is about 65 picometer, so it's pretty large. One thing that, however, as I mentioned earlier, there is some clear trend that we could establish with the data that we were able to collect. And we'll go on a little bit later to explain what are some things that we could have done processing-wise or growth-wise to sort of improve the compositional uniformity of these Project A samples. Moving on to Project B, here we see a lot less tacks. So this round of compositions that were of interest were able to grow a lot more easily, some of them being very close to the ideal atomic percentage, number 1 especially being one of our best crystals. Moving on to the UV-vis for these as well, we see that we have the insets of the pre-polished crystals, we have absorbance in the visible spectra, and the band gaps that we were able to get from the UV-vis were anywhere between, we don't have the images here, but some of them were as low as 1.37 if I'm not mistaken, all the way up to about 1.71. And here we have the EDS taken after polishing as well. So here we see that there's not as much of a difference with respect to the previous numbers. One reason we think why these synthesized a lot better is that first, there are already parent compounds synthesized for these, as we mentioned, the magnesium silicon phosphide, the zinc silicon phosphide, and the manganese silicon phosphide. Another thing we also suspect may be a contributing factor for the higher entropy phase incorporating or crystallizing a bit better, is the fact that we're kind of just working within the transition metal area, or the transition metal side of the periodic table. So the atomic radii difference is not as great with respect to the alkali earth metals. if I'm remembering correctly, the greatest difference is about 10 or 15 picometers. So there's not as much great disorder that allows for these crystals to crystallize in the high entropy phase. There was some trending data that we were able to get, specifically with magnesium and manganese. However, the relation is pretty weak with an R value of about 0.6. So probably a lot more synthesis and crystal growth will have to be done to validate whether this is a legitimate trend that can be established or not, but at least it's good preliminary data for the crystals that were synthesized.
All right, so yeah, in conclusion, for the on the computational side of things, we weren't, again, able to simulate the high entropy materials themselves. However, this is only due to some time constraints and the access to the computational resources that we had access to. That's not to say it can't be done. It's really just a matter of allocating resources to it. So besides that, we have the parameters locked down that we would need to simulate these materials and be able to see the sort of band structures, especially now that we have some experimental data on what kind of band gaps we can expect from them, just for some fine tuning of the parameters. But yeah, overall, just allocating more computational resources. For Project A, as Sam mentioned, we didn't get any truly high entropy samples synthesized, as most of that phase was lost in the polishing process. However, we were still able to gain some knowledge and insight onto the effects of changing magnesium to zinc ratios and how that affects the band gap in the material. And moving forward, we think it would be good to adjust some of the heating parameters, try a different flux maybe, just to help those larger atoms incorporate a bit better into the crystal structure. And also, I don't know if we mentioned it, we heard that the laser for the SHG was actually down this summer. So once that is back, we would love to collect some data on second harmonic generation just to confirm the nonlinearity of the crystals. And for Project B, we actually were able to get these high entropy materials synthesized. However, the compositional percentages, we weren't able to super tightly control like we had hoped. So we think that attempting to adjust systematically the molar compositions of each of the atoms one at a time might help us to sort of investigate how the band gap changes. And if not, like I said, again, the simulations could also help a lot to sort of see why these band gaps were lower and how the different elements would affect the band gaps with those density of state plots. It would be very useful to be able to simulate these materials. So that's all we have. We would like to thank Dr. Mao's research group, especially our mentors, Yasu and Sam. Big thanks to Dr. Redwing, Kelsey, and all the staff at MSc for providing us this opportunity. And we hope that it was as beneficial to you all at Penn State as it was to us.
Great, thank you so much. Yeah, I should have mentioned that, yeah, in addition to the bulk facility, they also worked in our theory facility. So we have some time for questions. So questions from the audience, either in person or online.
If I may, I think for the sample in the series A, in your UVVs, there was also some absorption peak in infrared. Is that correct?
Right.
Yes.
Not for
Repeat the
this
question
one.
again.
So I think for one of the graphs, maybe for the next slide, yeah, can you switch to the slide 17? Oh yeah, 17, right. So there are peaks at around 1500 nanometers or 1200 nanometers. Do you know what causing those absorption peaks?
Not exactly.
Honestly, we're not too sure what might be causing the absorption in those peaks.
Yeah, it is kind of strange because, again, these do just have the same elements that was present in the previous two samples. So, and we're not really sure what might be causing the slight absorbance there.
Are these samples conducting?
Conductive.
Are they metallic?
I don't think so.
No, they're not.
They shouldn't be.
They're not. Right.
All right, other questions? Are there any online questions? I don't know, Kelsey, can you see?
There are not online questions right now.
That's totally fine. I just can't really see from this one. All right, well, if not, let's thank Sam and James again. Well, I think Anna just left.
We could go to Amit then.
So I think Anna might still be having technical issues. So Amit, are you? Is Amit
Yeah,
there?
she's
Oh no,
there.
there you are. Oh, Anna is there. Sorry,
Yeah,
you're
sorry.
signed in on a different person. No problem.
Yes, yes.
All right, are you? All right, so let's go ahead and go back to Anna again from University of North Carolina, Greensboro, working in our MOCVD facility.
Okay. Sure. All right, can you guys see my screen and hear me okay?
Yes, looks great.
Okay.
Thank you.
All right, so I'm going to be talking about the modulation of inherent properties of 2D devices by strain and doping engineering. I will be doping the material with chiromolecules, so I wanted to talk about what is chirality. It is an asymmetry between isomers resulting from the arrangement of atoms in the molecules. To the right in the picture are my two chiral molecules I am working with, and the asymmetry is noted by the red circles, where it is either behind or in front of the CH3. But the chirality causes changes in optical behaviors, electronic behaviors, and mechanical behaviors. I will be focusing on the optical behaviors of my chiral molecules when introduced to the TMDs. But how does this relate to the TMDs? You can induce the chirality in multiple types of TMDs by layering them with the chiral molecules and liquid exfoliating them in the presence of a chiral ligand in water or other solutions. They can be used for chiral optical sensors, filters, and devices for light manipulation and such. So my research plan going to PSU was to grow the TMDs using MOCVD and then to transfer them onto the desired substrates with hopes to introduce the chiral molecules while I was there, but I did not get to that. So these are my three plans. Plan one included putting the chiral molecules on top of the TMDs and then studying that structure. Maybe adding a layer of HBN, I don't know. And then the second plan was to intercalate the chiral molecules in 2 layers of TMDs. This could be the same, like 2 layers of MOS2, or changing them with MOS2 and WS2, or either or, and then to liquid exfoliate them. Before I went to PSU, I deposited my chiral molecules onto a glass slide and studied the polarized Raman spectroscopy of them. And we had changes in intensities and slight, very, very slight shifts when changing the polarization of the 2 chiral molecules, L and D PDI. L and D are just Latin terms that mean left and right. It has a long name, but I forgot them. Then I went to PSU and I learned how to grow them, grow the TMDs with Dr. Chin Chin and Dr. Andrew Graves. I did not actually grow anything because I was not there long enough to be able to learn how to operate the machine, but they grew these beautiful samples for me using the MOCVD system pictured on the left. In case you do not know how MOCVD works, I wrote a little description saying that the reactant gases are combined at elevated temperatures in the reactor to cause a chemical reaction. And during that chemical reaction, they form a layer of material on your growth substrate. And this is on the right 2 AFM images of grown MOS2 using MOCVD1. As you can see, they're multi-layer, and some areas are coalesced and everything is beautiful. And then I learned how to transferred the TMDs from Dr. Shalini Kumari while I was there. This is the process that I used. I focused mainly on transferring them and perfecting the transfer process while I was there. But I spin coated a layer of PMMA on top of the TMD sapphire. TMD is grown on sapphire, so that's why it's written as TMD sapphire. But I spin coated PMMA, let it dry, and yeah, and then I put it on the hot plate, attached a thermal release tape on top. And then once you put that system in DI water and sonicate for 5 minutes, it's easy to peel the thermal release tape from the sapphire, and the thermal release tape has both the PMMA and TMD attached to the thermal release tape. And then you can then attach that to a target substrate. In this case, it was silicon. And then once you heat it up, the bonds between the TMDs and the silicon attach, and you get a nice, beautiful layer of TMDs. And then since it's thermal release tape, once you heat it to the releasing temperature, it does release, as you can see in this little video at the bottom right. The tape is releasing from the PMMA, TMD, and silicon. And then that can be easily peeled away like that. This is what my transferred TMDs looked like. I got a pretty large area of transfer with, of course, holes and rips, because not every transfer is perfect as the growth, of course. And then as you move down, you could see that the same structures are there from the TMD, with the inclusion of PMMA residue left behind of about 20 nanometers in height. Okay, and then when I came back to JSNN, I decided to start adding the chiral molecules. So I have the left and the right. This is the left chiral molecule that I'm showing here. So to add the chiral molecules, what I did was I took my MOS2 and UV cleaned it for 2 minutes to remove all excess contamination and free the bonding up for the chiral molecules. But that did not change the structure. That's what I'm showing with the left images. And that's before and after deposition. And then for the ramen, before was just the MOS2 peaks, but now we can see the ramen has the chiral molecule peaks that were showed in the preliminary work, and then the silicon peak that was not there because the chiral molecules were sitting on glass before. And these are all the labeled peaks. And then my next steps will be to do polarized Raman spectroscopy on these, on this system, and then do the 2 other plans, plan 2 and plan 3, and then analyze everything and optimize it. And I did not add an acknowledgement slides because I forgot, but thank you. Do you have any questions?
All right, thank you, Anna. Does anybody have any questions, in person or online folks? Okay, actually, I had a question. I was hoping nobody would. So when you deposit the chiral molecules on the TMD, do you know if they like align with the TMD in some way, or are they just totally randomly oriented?
They're just randomly oriented. I don't know if there's a way to control that because they're super small, but I don't know.
Okay, yeah, I was just curious. Are there other questions in person or anybody online, Kelsey? No? All right, let's thank Anna again. All right, so our next speaker will be Amit Shringi from North Carolina Central University, and Amit was here this past summer in our Thin Films MBE facility.
Sure. Thank you.
All right,
Thank
Amit, whenever you're ready.
you. Sure. Is my screen visible?
It's still thinking, hang on. We just see a black screen, so.
Is it visible now?
No, we still just see a black screen. We don't see a slide or anything.
Do you want to stop your share a
See the
minute and
slides on
try
my
to
end.
share? Yeah, I can see it on the
Oh.
laptop, but we can't see it in the room.
Yeah, so can you just try again, Amit? Ah,
There we go.
perfect. Great,
Thank you.
thank you.
Hey, yeah. Good afternoon, everyone. I'm Amit Kumar Sanghi. I'm postdoctoral researcher in North Carolina Central University. I was there a RSVP fellow during last summer for 3 months. My project title was optimizing broadband photo detection with thickness modulated MBE-grown bismuth chalcogenide thin films and heterojunction. In this regard, first I would like to tell what we were targeting. We were targeting like shortwave and midwave IR photo detection. Like why midwave IR detection is important because current technology, which is which needs thermal cooling to detect the midwave IR radiation, and that's why we want to put semiconducting material which don't need the thermal cooling for the efficient midwave IR radiation detection. So we choose the bismuth chalcogenide. The atomic structure shows the quintuple layer thick bismuth chalcogenide, and they have van der Waals force between each quintuple layer, so they are 2D material. They can be exfoliated in terms of one quintuple layer, and the image shows the uh, direct uh, direct cone separation at the lower quintuple layer, and as we increase the thickness of bismuth chalcogenide, the quintuple the band gap merge and it forms a direct cone. So this phenomena, with the increased thickness, the interlayer interaction which forms the multiple interlayer hybrid quantum states, which leads to merge of band gap and leads to formation of topological insulator. This phenomena we want to use, and we want to see the effect of this phenomena on photo detection property. Based of my knowledge, no one have explored it so far in a controlled manner. So in this regard, we grown bismuth selenide, bismuth telluride, and antimony telluride samples. We select sapphire and mica substrate. For the bismuth selenide and bismuth telluride, we grown 3, 5, 7, and 10 nanometer sample for our studies. We also grown few samples for optimizing the thickness. Those were like 21 nanometer for bismuth selenide, and for bismuth telluride that was somewhere around 63 nanometer. The growth temperature was kept 220 degree. We optimized it in the range of 200 degree, 220 degree and 240 degree. We get the best result at 220 degree centigrade. So we choose this for the rest of our sample preparation. These are the read pattern for the grown bismuth selenide sample with the different thickness 3 nanometer, 3 nanometer, 3 quintuple layer, 5 quintuple layer, 7 quintuple layer, and 10 quintuple layer. This 5 quintuple layer sample was behaving abruptly. I don't change because I don't get chance to repeat the AFM while coming back here. I'll still trying to get AFM done, but this is the data with the old sample. So we found that with the increased thickness, surface roughness was getting reduced. But for the 5 nanometer sample, the surface roughness was the read pattern shows the uh, brightest pattern of the brightest stroke of read. Uh, and the same thing we confirm with the Raman and UV, but we repeat this experiment and we get the exact thickness, and rest of the data was in a trend. So here we can see we did the Raman with 532 nanometer using 532 nanometer laser, and we see a shift with the increased thickness In the A1G mode, which is out of plane vibration mode, we observed a increased absorption with the increased thickness of bismuth selenide layer. The XRR data shows the trig interpolayer thick sample, which shows it has thickness of 2.83 nanometer. This is the read pattern and AFM measures for 3, 5, and 7 quintuple layer. Here we also observe a 10, which is showing 1.14 to 1.69 nanometer surface roughness, average surface roughness for the as we increase the thickness of bismuth telluride samples. Here we also observe a blue shift in the A1G mode, which is again out of plane vibration mode for bismuth telluride. And similarly, we observed a increased absorption which for the bismuth telluride sample, and which is more in near IR region in compared to bismuth selenide, which shows the bismuth telluride have a lower band gap than bismuth selenide. And with the increased thickness, we are getting higher absorption. This phenomena, like this kind of trend, I want to realize in terms of devices. So for this, we prepared the devices with the different channel length from 3 micrometer, 5 micrometer, 7 and 10 micrometer. I characterize the 5 nanometer thick bismuth selenide sample with 5 micron channel length using our 780 nanometer and 1515 nanometer LED light. And we've seen a good photo detection data. Like the data shows that with the dark, the current was very less. It was in the range of somewhere around 10 nanoampere. But with the 780 nanometer, we see a good photo detection current. And the photo current was for 780 nanometer was relatively higher than 1550 nanometer laser. And the same current versus time characteristic we observe for the 780 nanometer and 1550 nanometer LED light. So in the next now comes to like what I'll going to do with the prepared sample. So I'll perform the systematic photo detection analysis for the prepared devices. Later on, once after finishing the photo detection analysis, I'll use those samples for charge transfer property analysis with the integration of TMDs with by making heterojunctions. And the bismuth selenide and bismuth telluride samples I'll use for gas sensing performance analysis with slight modification, maybe with the decoration with 0-dimensional materials. I would like to acknowledge few people or facility behind this program, which give us the opportunity to explore different avenues and huge facility of Penn State. I would like to acknowledge NSF2DCC MIP facility, Material Characterization Lab facility, Nano Fabrication facility, Penn State University. I would like to acknowledge Professor Nitin Samar to host me, to give me opportunity to conduct my research work at their lab. Dr. Stephanie Lowe for assisting me for like providing me the FTR characterization facility, and Dr. Ron Redwing to review my project at the initial level. I would like to acknowledge my deep sense of gratitude to Dr. Anthony Richardella, Dr. Yong Xiu to support me during my stay, to help me learning the MBE technique, the XRD technique, and the members of Nitin Samar's lab. I would like to acknowledge Professor Fayan, who is supervisor here in NCCU. At the end, I would like to acknowledge the support of Kelsey Maxine and to this CC staff during our stay there. So now I am open to questions.
All right, thank you, Amit. Are there questions from the audience here or online?
None online.
So Amit, what's the first gas that you want to try to do your gas sensing?
bismuth selenide is reported for nitrogen oxide, dioxide, NO2.
Mm-hmm.
So I would like to try that, but my target will be like to get a room temperature sensor.
Mm-hmm.
So I would look whether it is suitable for the room temperature detection or not. If it is not, I'll use a zero dimensional or lower dimensional material over it to decorate for a electronic sensitization where we can get a good sensing result by the spillover effect for NO2. I want to target it especially for the NO2 gas.
Got it. Thank you. Any other questions from anybody?
I mean, still the data was like, I had a lot of data, but for this limited time, I think it was not.
All right. Let's thank Amit again. All right, and our final speaker is Jonathan DiStefano from the University of Washington. Jonathan was here last summer working in our materials transfer facility. So whenever you're ready, Jonathan, go ahead.
Yeah, hi all. Hope you guys can see my screen and stuff.
Yes. Yep, looks good. Thank you.
Okay. Yeah, so today I'll be talking about tantalum nickel tellurium 235, an exfoliable quasi 1D semiconductor. And I'd like to start this with motivating a bit why I actually came to Penn State. In my lab at UW, I'm interested in bulk crystal growth and then electrical transport measurements. And I'm particularly interested in magnetically or electronically ordered phases, like charge density waves, ferromagnetism, stuff like that. But of course, to learn anything about these different materials, you have to have some tuning knobs to actually change them so that you can study them systematically. And so we use kind of the standard tuning knobs of condensed matter physics now, of low temperatures and high magnetic fields. But because we're a crystal growth group, we're able to do chemical substitution. So we can tune magnetic interactions, change the Fermi energy, things like that. And then kind of what the lab I work in specialty is applying uniaxial stress in situ. So we have a bunch of different tuning knobs to change these bulk materials, but I was interested in learning more about more tuning knobs. And so that brings us to Penn State, where I was actually working on 2D materials, or van der Waals materials, of course. And so these have these strong in-plane bonds and weak out-of-plane bonds. And because of this, you can kind of cleave them repeatedly and reduce the number of layers that you're looking at. And there's a lot of different reasons to do this. A few that I've mentioned here. First off, this idea of reduced dimensionality. So of course, if you take a piece of graphite, like is used in pencil lead, that is going to have very different electrical properties than a monolayer of graphite or graphene. Another reason these have kind of caught a lot of attention recently is this idea of artificial materials, where you can take, few layers of different materials and stack them and make some sort of designer crystals that you can't make otherwise in a bulk crystal. And last one I'll mention here real quick is just that we have more tuning knobs that I've mentioned. We have the ability to electrostatically gate because we've reduced the number of carriers in the system by reducing the dimensionality like this. And if you have the right gate set up, you can also apply a vertical displacement field and kind of localize your electrons in different vertical areas of your crystals here. So there's a lot of different things you could do with these 2D materials. And so now to talk briefly about the actual production of 2D materials, which is what I was learning about this summer. You guys have probably heard about the idea of graphene being produced by Scotch tape. So basically you take a van der Waals material, you throw it on some tape, you fold the tape over, you peel it back, and now suddenly you have copies of this material. And if you do this repeatedly, you'll end up with a bunch of copies. And some of these will be different thicknesses than others. And the idea is you can then put this onto silicon, and if you peel up this tape slowly, hopefully you'll get some thin flakes that are left behind in the silicon, which you can search for with an optical microscope, like shown here on the right. The different layers will kind of have different colors. And you can verify what your eyes are seeing, as well as determine the actual thickness by using an atomic force microscope, where you're kind of dragging this cantilever along the silicon substrate. And when you feel the presence of some flake, the cantilever will move, and then you can figure out the height that it moved, and thus the height of your flake. And so in this, we have now taken bulk crystals, which are for order, millimeters squared by hundreds of microns, and made them into hopefully thin flakes, which are on the order of microns squared by nanometers, hopefully. So this is quite a powerful technique despite its simplicity. And so the reason that I really wanted to come to Penn State was this, the 2DCC inert atmosphere cluster tool, which conveniently you could do all the steps I just mentioned inside of a glove box with an argon atmosphere of less than 0.1 part per million water and oxygen, which is very important because these kind of new materials that I'm interested in often get very air sensitive as you thin them down. And so if you're just doing it in air, you'll do all this work and you'll be left with nothing. Whereas if you do it in a glove box, hopefully your flakes will be more or less safe. And so the system of interest, like I mentioned earlier, is tantalum, nickel, tellurium, 235, or TNT as we like to call it. It's this kind of quasi 1D van der Waals material, so you have these long chains that are running through it. And it seems naively like a very boring material. It seems like in bulk, it's just a paramagnetic, completely trivial semiconductor. And so you might ask, why are we interested in this material? And it turns out that the very similar sibling compound, where if you remove the nickel and throw in palladium to form tantalum palladium tellurium 235 or TPT, is actually a very interesting material. It's a potentially a higher order topological insulator. People have kind of observed that in experiment. And then also people have seen signatures of it potentially being a bulk excitonic insulator. And so without really motivating any further these buzzwords that I've just thrown at you in the sake of time, we can ask, is there any way that we could tune TNT to be as interesting as TPT, since they seem so similar? And so the way we went about this, or wanted to start going about this, was through exfoliating this material. So I grew the crystals back in my lab at the University of Washington. I brought them to Penn State, and then in the glove box system I was showing you earlier, we could exfoliate and search. June Zhu's group, who I worked in, they were kind enough to provide me with some pre-deposited contacts that were comprised of gold and titanium. So if you pick up your flake using kind of dry transfer techniques, you can align it using the transfer stage in the glove box over your pre-patterned contacts. And you can place down a flake and then cover it with a polymer to protect it from air when you remove it for actual measurements. And so this technique allowed me to make these very simple devices relatively quickly and do a coarse thickness dependence and see how the resistivity changes as a function of flake thickness. And so what I'm showing here on this slide is some preliminary data I took at Penn State. So I have the normalized resistance, normalized such that it's 1 at room temperature as a function of temperature for several different thicknesses. And we can see that broadly, it seems as we thin this material down, it gets less and less resistive at low temperatures. In particular, if we look at high temperatures, where these seem to be acting as just kind of boring semiconductors, we can fit this data to the Arrhenius equation, which gives you something that is like the band gap, something proportional to the band gap. And what we see is that not monotonically, but a trend that could very clearly be seen is that as we thin this material down, it gets less and less insulating, and the band gap gets smaller and smaller. And so this seems to be to us that this system may be metallizing it as thinned down, and so perhaps in thinner flakes, a true metallic state or a new, now inverted band gap could be realized like is seen at TPT. And so now current work, I found at Penn State thinner flakes. So the thinnest one I showed in the last slide was 9 nanometers, but I actually managed to see a tri-layer a few times, which is about 2 nanometers. But unfortunately, due to the geometry restrictions of the pre-deposited contacts I was given, I was unable to make devices with these. But now at the University of Washington, I'm working in collaboration with Professor Xiaodong Xu's group, who is really at the forefront of this kind of 2D stuff. And we're using some, fancy photolithography techniques to actually make devices with these thin flakes. And so, for example, this week, I've been making a 3.5 nanometer dual gated device, which should allow us to see kind of some more interesting stuff. And so some key takeaways here. Over the course of the RSVP program, I learned the basics of 2D device fabrication. We have some preliminary results that I got that showed that with decreasing thickness, we seem to be metallizing the system. And now with my new skills, I am working to make thinner devices back home at the University of Washington. And so I'd just like to thank Professor Jun Zhu, her student Carlton Drew, and her postdoc Yongyang Chen for hosting me. I really appreciate their help this summer.
All right. All right. Are there questions for Jonathan?
Yeah, it's just how sensitive to oxidation are these? If you were to expose these exfoliated samples to the atmosphere, what happens to their properties?
So I had a collaborator actually exfoliating these at first, and he found that 20 nanometer flakes did not really change much. But I actually found a bilayer the other day, and we accidentally exposed it to air, and it was gone in like an instant. So as you thin it down, it gets quite air sensitive quite quickly.
So how are you going to determine if these are topological materials, right? These flakes are quite small. I don't know if you can really do ARPEs on them. So how would you know?
You could technically do like micro ARPEs or something, which Dave Cobden's group here at UW occasionally does. But kind of an easier way is Xiaodong's group does these kind of sophisticated optics measurements, and they can learn about the nature of a band gap through that. So for example, in Twisted MOTE2, they recently used optics to actually tell that it was an inverted band gap before doing transport measurements.
Nice. All right, any other questions?
I guess, just, have you done any magnetotransport measurements and looked for weak anti-localization or anything like that?
Yeah, so I did some magnetotransport measurements this summer, and there is some weird cusp-like behavior at low field, but unfortunately the PPMS I was using, it was a little bit noisy because I was using the internal resistivity option. So I'm going to actually redo those measurements here at UW.
Any further questions from anybody? All right, if not, let's thank Jonathan again. All right, so that concludes the 2024 2DCC RSVP Symposium. So just want to remind everybody listening, if you are interested in coming to Penn State for your own RSVP training experience, the deadline is the end of January. If you have any questions, please feel free to contact me or Kelsey. And thank you to all of the RSVP participants who gave some excellent talks today. And thank you all for attending. Great, that's that.
Thanks, everyone.